In this video, I'm going to talk about how to deal with the problem of autocorrelation in linear regression. Oftentimes, when you are building a linear regression model for forecasting purpose and you have predictor variables which are time series in nature, you will come across this problem of autocorrelation, which is going to create quite a number of issues in interpreting your estimates, and we'll see how do we detect such problem and how do we deal with it. So what happens when there is autocorrelation? Well, what we mean by autocorrelation is that when you build a regression model, the error terms need to be completely independent of each other. You cannot have a linear regression in which the error terms are correlated. So the assumption in linear regression is that the error terms should be independent. They should not be correlated. If at all they are correlated, then we come across the problem of autocorrelation. So if the violation happens, we need to detect if at all there is presence of this problem, and we should find out a way to eradicate before we can come up with the final regression equation. So here is a linear regression equation. It's an example of an equation in which we would come across this case. Not in all cases though, but we have chances of facing this issue in such cases. So here is this equation. We have got a dependent variable which is time series in nature, and most importantly we have the independent variables which is also a time series one. And in such cases where the independent variable is time series is in nature, you most probably come across cases of problem of autocorrelation where the error terms would be correlated to its previous error terms. So how do we detect and how do we eradicate? Well, just to see an example, I can show you what is an uncorrelated error terms and what is a correlated error terms. When you have uncorrelated error terms, your error terms will be randomly distributed across the origin. So when you build a regression model, y equal to beta naught plus beta 1 x, and of course there is t, and you have error term, right? So your error term, when you plot it across this origin, it should be completely random. In such cases, we say that the error terms are uncorrelated and there is no pattern in the data, no pattern in the error terms. Whereas if the error terms are correlated, you will find some sort of a pattern. Now in this case, you can see the error terms have some sort of a pattern. It is growing and then it comes down and then it goes again. And that's a typical case. That you can find it out graphically or just by plotting it out. But there are statistical ways to find that also, and we'll see that. So this is an output from the SAS. So this is a typical example of autocorrelated time series where you can see the error terms have some sort of a pattern. It could be upward slope, downward slope, and having both upward and downward slope. So that is a typical case of autocorrelated error terms. We can use statistical tests to find out if there is a presence of autocorrelation in the error terms. So the famous one is the Durbin-Watson test, and the most popular one, I would say. By using Durbin-Watson test, we can find out the first order autocorrelation. So what is first order autocorrelations? We assume here that the error term ET is just a linear combination of its immediate error term. So ET is just a linear regression of ET minus 1, and of course there is an error term. So the error term itself is a function of just its previous, it's one lag of the error term. So et is some sort of a function of et minus 1. So et is a function of its previous lag, or just one lag below it. Okay, so that sort of a relationship, autocorrelation, can be found out using Durbin-Watson. Okay, so this is a typical case of autocorrelation which can well happen or well found out in a linear regression model, and using DW test we can find out if there is a presence at all. Of course, there is an assumption here that rho, which is just an estimate for this linear regression, is less than 1 for this particular series to be converging in nature, and the error term is normally distributed. It's a white noise process which is normally distributed with mean 0 and variance of 1. So we'll see how do we perform the DW test to detect the autocorrelations. The DW test goes like this. We have this null hypothesis which says that rho, remember what is rho? Rho is just the estimate. So we just a linear regression, okay, linear regression of the error terms. Now you might wonder, from where do we get this epsilon t? Remember the equation that we saw in the first slide? We had this equation, right? Yt equal to if I could just take you to the first slide. Alright, so this is the equation, and every regression equation has an error term in place. So we have taken this error term and we are showing here that error term itself follows some sort of a linear regression. So all you need to know, what is this rho, what is this estimate behind this lag of the error term. If this is not significant, the idea is to show that this is significant. If this is not significant, this is 0, then your error term is not correlated with its lag. If it is non-zero, only then it is correlated. That's the idea, and we'll see how we can statistically show the relationship. Alright, so the DW test has the null hypothesis rho, which is the coefficient of the lag term is 0, and the alternative hypothesis is that the coefficient is non-zero. Now if this is accepted, then there is no correlation, no autocorrelation. If this is accepted, the null hypothesis is rejected. Then we'll have to accept the fact that there is presence of autocorrelation among the error terms. The DW statistics is defined like this. Okay, this is just a formula. We wouldn't go into the details of the formula, but I'll just tell you what exactly is this formula. Well, this formula, so we have got the error term here. And this is just a notation. Okay, just don't be confused with et and epsilon t. So we found out the error term from here, and we just put it in this particular statistic, and we calculate what is known as the DW statistics. Okay, so it's easy to count because finding et is easy. It's just yt minus yt hat. It's just the error term in any linear regression equations, and just put it. Okay, just put for all the all t starting from t equal to 2 to t equal to n. Depending on how many error terms you have in a regression equation, you can find out this particular numerator, and you also have the denominator in place. Just add them all, divide the numbers, and you will get the Durbin-Watson statistics. Okay. Theoretically, what it means, we will not get into the details of it, but we will see this statistics is going to help us finding out whether the estimate is significant or not, and based on which you can decide whether there is presence of autocorrelation. Alright, so when you use any of the statistical softwares like SPSS, SAS, R or MATLAB, you will find out the p-value of rho. Now when you find out the p-value of rho, you can easily get to know whether rho is statistically significant or not. If p-value is less than 0.05, so it's statistically significant at 95% confidence level. Okay, and if it otherwise, then it is not statistically significant. Okay, and based on that, you will make an inference. And remember one thing: if the rho is significant, only then you can be sure of the fact that there is presence of autocorrelation. So if at all there is a presence of autocorrelation, it is going to be problematic. You cannot use an ordinary least square regression equation in order to be able to build a forecasting model. You'll have to do some remedial measures before you can use this data for forecasting using linear regression. One of the simple way to handle autocorrelation is just omit a key predictor variable. So first one, omission of a key predictor variable. Okay, you have several independent variable in place. One or more than one variable could be the reason for autocorrelation. Just try it out randomly, and you probably can get rid of the problem. It's not as simple though, and most of the times this simple way of eradicating or remediating this problem is not going to be effective. So you need to do what is known as variable transformation, and that is much better way of handling autocorrelation. So there are two ways to handle, do the variable transformations. One is the Coursera-Orkut procedure. Not able to pronounce correctly, but it's we just call it as CO procedure. Okay, the Coursera-Orkut procedure, and the second one is the first difference procedure. In the CO procedure, what we essentially do is that we have this equations for error terms, and all we are interested in is to know the whether rho is significant or not. With Durbin-Watson statistic, now we are sure that there is presence of autocorrelation. Now we are sure that rho is significant. It's a non-zero value. Okay, so the first step is done. There is presence of autocorrelation. The next step is how to eradicate. Okay, so we just need to do some sort of a transformation. Well, for what transformations are we doing? So the original equation is like this: yt is beta naught plus beta 1 xt1, beta 2 xt2, and so on. So what we'll do is we'll just do the transformation of both dependent variable and each one of this independent variable. Okay, so how do we do the transformation? So we say that yt star, which is a transform variable, is equal to yt minus rho hat. Remember, this is already already we have found out what is the value of rho, and we have found out that this is significant enough. So yt minus rho hat yt minus 1. So this is the transformation we are making on the dependent variable. On the independent variable xtj, we are making transformation pretty much the similar way: xtj minus rho hat xt minus 1j. So it's just the we are just subtracting by multiplying the rho hat and its lag, right? yt minus 1, and just we have multiplied rho hat to yt minus 1. So it is some sort of a transformation that is going to help us reducing the problem of autocorrelation. So instead of regressing yt with xt1, xt2, xt3, we will do the regression with the transfer variable. Okay, so this is the new variable or the transformed variable. This is also the transform variable. This is independent one and this is dependent one. So we'll regress yt star with xtj star instead of the original equation. So we'll just replace yt with yt star and xt1 with xt1 star, x22 star, xt3 star. Alright. Now the question is, how do we get back to our original estimate? Mind it, our original estimates are beta naught beta 1, not the beta naught star beta 1 star, because these estimates of course will be coming from the transform variables. So the slope coefficient, the intercept, the beta naught 0 can be found out like this. This is star. So beta naught, which is the main variable or the original estimate, can be found out by beta naught star divided by 1 minus rho hat. Okay. Whereas the slope coefficients are always going to be same. The reason is because we have done only a linear transformation, okay, a parallel transformation. So it is only going to change the intercept, not to the slope coefficient. When you do a linear transformation, your regression line will, if this is the original regression line and you do a transformation, it is probably going parallelly. Okay, this is a transform one. So it has only changed the intercept, not the slope. The slope has remained same. So the beta, slope coefficient beta 1, beta 2, beta 3, they are same. It's exactly same as the transform, what you get from the transform variables. Whereas the intercept is going to change, and it's going to change by some amount, and that's exactly the amount. Beta naught equal to beta naught hat equal to beta naught hat star by 1 minus rho. And remember, we already have this value in place. Alright, so that's the first way. A much easier way is the first difference one, and this is often encountered in many forecasting models. So we just assume what we learned in the last slide. We just assume that rho hat equal to 1. The estimated value of rho is just 1, okay, all the times, and we just put that in the equations. Our initial regression equal to is this. Just put that in the regression equation for error terms, and it remains exactly the same. So we do the same transformation. So initially we had rho here, right? Now it takes the value of 1, so we just need not have to write this. Okay. Similarly here in the independent variable, so we do transformation of yt and xtj with pretty much the similar way we did with the previous one, the CO transformation, except the fact that here we are assuming that the rho takes a value of 1. When rho takes a value of 1, technically we call it as first order autocorrelation. First order autocorrelation. So first order autocorrelation can be eradicated or can be handled by taking the first difference. If you're familiar with time series ARIMA model, this is very common thing to do there. Okay, when you do build a ARIMA model, you often come out with this problem of serial autocorrelation. You remove them by doing different type of transformations, first difference, second difference, so on. So in a typical first order autocorrelation, you would remove this with first difference. Okay, first difference is nothing but just a keyword for saying that yt minus 1, just subtracting from subtracting the lag from its value. That's exactly it is. And when you do that, you have the transform variables in place, yt star and xtj star, and you do the regression instead of doing it with the original variable like yt and xtj. Once you have the estimates in place, it's going to be for the transform variables, right? So how do we get back to the original estimates? Okay, because initially we had yt equal to beta naught plus beta 1 xzt. Now we transform variables. We have yt star equal to beta naught star plus beta 1 star xzt star. Now with transform variables, we are only going to get beta naught star, beta 1 star. So how do we get back to beta naught and beta 1? Alright, so in this case the slope coefficient will remain same, because again this is some sort of a linear transformation. It's not going to change the slope of the regression line. So we've got the slope coefficient, and using this particular, when you you can use the mean equations in order to be able to get what is the slope coefficient. Okay, so use this equation, you will be able to get what is beta naught. Just plug in the values of all these betas, beta 1, beta 2 up to beta p, number of, depending on the number of variables, you will get the slope very easily through these equations, from these mean equations. So now we have learned how to handle or how to get rid of the problem of autocorrelation, how to detect it first, and then how to handle it next. But autocorrelation sometimes, in fact, it is helpful many times in forecasting, and ensure that you make use of having your regressive errors in a forecasting, and it ensure that you you include that in forecasting while you're building a forecasting model. So typically your estimates would look like this: y hat t equal to beta naught plus beta 1 xt. Okay, but this should not be your forecasting thing, your forecast value. This should not be. Okay, so the updated forecast would be ft, let's call it as ft, and that is just estimated yt plus the error term. So you're using the error term to get the final forecast. And when you have the first order autocorrelation, you can just add this one. Instead of et, you just put rho et minus 1. Okay, depending the order of autocorrelation. We have only discussed the first order autocorrelation. Remember one thing: it can be of any order though. Oftentimes it would be first order, but there are times when it is not the first order. It could be just any order. We'll see that in another video, in another session. Thank you so much.